All right, section 8.4 is on applications of the normal distribution. All right, so we learned what a normal distribution was. We learned previously that if we have a standard normal distribution, that right here in the middle we have z equals 0, or the mean equals 0, and for a standard normal distribution we had that sigma was equal to 1. So we really didn't do much with the z-score formula. Z equals x minus mu over sigma, because all of the problems that we were looking at, if mu is 0 and sigma is 1, then z was simply equal to the x value, just whatever number they gave us. So that does change, though, if we don't have a standard normal distribution, because not every data set in the world is going to have a standard deviation of 1 and a mean of 0. Okay? And so what we have to do to be able to use our tables that we were using and to be able to use our area under the curve and draw our pictures correctly, we need to change the values over whatever we have to a z-score. Okay? And a z-score, if you remember when we were looking at our tables, that was table A and table B in the appendix. They are attached to your formula sheets that I gave you. There was one sheet that was negative z-scores and one sheet that was positive z-scores. And every z-score is rounded to 2 places. And then the areas, or the numbers inside of the table, correspond to the area under the curve from left to right. Okay? So, for example, when we looked up, if we had a z of 1.00, that will be to the right here of the middle, because the middle is 0. So if I was looking at 1.00, if I look that up in the table, it's going to give me the area of everything from the right all the way up to that value. And that area corresponds to a probability. That's why we're doing this, to figure out probabilities. And so if we did look that up in the table, let's see. That would be on table B. And 1.00 gives me 0.8413. So 0.8413 would be the probability that you could say x or z if we were using a standard normal distribution, but z is less than 1. All right, what we were doing, it was x, right, because our x was equal to z. But still, the probability is 0.8413. That means that about 84.13% of the area under the curve here is shaded. Okay, and so that's basically what we did the other day. We figured out that for less than problems, we'd get area to the left. For greater than problems, we would be looking for area to the right, which we would have to say 1 minus the value that's given to us in the table. And then if we wanted to find the area between 2 values, we had to find the area of the one on the far right and the area of the one on the far left, and subtract the right value minus the left value, and that would give us the area between the two. Okay? So we will be using our z-score formula a lot in this section. Okay? So this z equals x minus mu over sigma, that transforms any normal random variable into a standard random normal variable. Okay. For example, let's say that we wanted to work, let me find us a little problem to do. Here's one from the PowerPoint. and I know that the PowerPoint explains how to do it. I'll just try to go into a little bit more detail. Alright, so it says find the probability that a normal random variable with a mean of 10 and a standard deviation of 20 will lie between 10 and 40. And these are x values, so we're not given like any meaning of what this actually is. They could be really anything from any data set. We are told that the mean is 10 and the standard deviation is 20. So we need to know those so that we can figure out the area between the two. We figure out the area between the two by converting over our x values into z-scores, and then we can find the area of the one to the far right, the area of the one to the far left, and then say the area of the one to the far right minus the one of the area to the far left. So we've got to work out two z-scores here. So first let's work out a z-score for an x value of 40. So that would be z equals, remember it's x minus mu over sigma. So 40 minus mu is 10 over sigma. And sigma is what? 20. That's our standard deviation. Alright, so that's going to be 30 divided by 20, or 1.50. Alright, so if I look up in my table a value of 1.50, that will give me the area from all the way here on the left all the way up to that value. Okay, so let's look that up in our z-score chart. That's going to be on table B. On table B. Alright, so I got 0.9332. So that's an area of 0.9332. So if I had all this shaded here on the left, all this shaded, and then all this too, that would be 0.9332. Or about 93%, 93.32% of all the area under the curve. Alright, now let's figure out a z-score for 10, an x value of 10. So it's x minus mu over sigma. 10 minus 10 over 20. Well, that's 0 divided by 20, which is 0. So now, if I look up a z-score of 0.00, that's going to give me the area from the far left all the way to this data value. You could probably guess it by just looking at it, because 10 is the x value right here in the middle. And we know that on one side of the middle and the other side of the middle we have the same area. But let's look it up anyway. 0.00. You get 0.5000. So our area here for a z-score of 0.00 is 0.5000, right? So all of this to the left, all of this is half the area under the curve, because we know that all of the area under the curve is equal to 1, right? So to get our answer, to find our probability, so this is the probability that our random variable is greater than or equal to 10, but less than or equal to 40, is going to be equal to 0.9332 minus 0.5000. Okay, and so if you do that, you'll get 0.4332. So that's our probability that the random, or that our normal random variable will lie between 10 and 40. All right. Now again, I know these problems don't have a lot of meaning because they don't have any, we're not talking about age or weight, but this could all, be We could be talking about IQ scores, we could be talking about cholesterol levels, we could be talking about temperatures. So all of this, if we have a data set and we know a mean and we know a standard deviation of that data set, we can figure out the probability of, say, that a randomly selected person has a temperature of 97.3. You know, so we can figure things out like that by using Z-scores. Let me see if I can find a problem that's a little more, I guess has a little more meaning or is a little more fun. I guess fun is relative though. Alright, so here's one, again, that has a little bit more meaning. This is from your ebook. All right, read this problem real quick. All right, so now from that problem, I want you to write down the mean and the standard deviation. All right, so what's our mean? Our mean is equal to, all right, 234. Our standard deviation is equal to 94. We want to know the probability that the next purchase will total between $100 and $150. Okay, so if anytime we're trying to find between, a probability between two values, that's when we're going to have to do two Z-scores. Okay, so let's first do the one for the bigger number. So we're going to let x, for the first problem, I'm going to let x equal 150. And my formula is z equals x minus mu over sigma. All right, so that's z equals 150 minus, what was the mean? 234 over 94. All right, so I'm going to need to do that in my calculator. And I want to round that to 2 decimal places. So that's going to be negative 0.89. Okay, so we want to look up in our Z-score chart. So you need to flip to the side where it's negative. And we want negative 0.89. So negative 0.8. And then the 9, if you look at the top, you can see the 0.09, that's the first column on this table. So that would be 0.1867. So my area here is equal to 0.1867. All right, now let's figure out a Z-score for 100. So for 100, we'll have x equals 100, z equals 100 minus 234 divided by 94. And if I round that to 2 decimal places, I get negative 1.43. All right, so let's look up negative 1.43. Now remember, the hundredths place, you're going to have to go over to the 0.03 column. All right, so I got 0.0764. Is that what everybody got? We have to be able to read these tables. All right, now if you're ever confused when you have a between the problem and you're not sure which one to subtract from the other, remember this is area under a curve, and area can't be negative. So if you choose the wrong number to subtract, like if you say the smaller number minus the bigger number, you're going to get a negative answer. And you can't have a negative area, and you can't have a negative probability. Okay, so even if you don't have a picture, which I could draw a picture now, and it would just be kind of a guesstimation. You know, here's what my guesstimation picture would look like. If I know that z equals 0 is right here in the middle, that's where the mean would be. That's where x equals 234. Then negative 0.89 will be to the left of that, because negative numbers are to the left of 0 on the number line. So it wouldn't quite be to where negative 1.0 would be, but it'd be somewhere almost one standard deviation to the left, because that's what these z values are, standard deviations. So I'd have one about right here. I could just pretend it's about right here. And then negative 1.43, that's going to be even further to the left, because remember how the number line works. The further to the left you go, the bigger the negative numbers get. So I'd say it's probably going to be about right there. I'm just going to, again, these are just guesstimations. But I'm trying to find the area between those two. And you can see it's probably a pretty small area, because if the area under the entire curve is 1, then that's just a little piece of it. So to get my answer, I'm going to say the area furthest to the right minus the area furthest to the left, so it's 0.1867 minus 0.0764. So that's going to be I got 0.1103. All right, so there's about an 11% chance, 11.03% chance that the next purchase will total between $100 and $150. Now, let me show you something real quick. These tables are also in your homework. So when you're going through your homework, that's what I did, was just pull up a homework problem, and we're going to do this one next. If you need the negative z-score table, if you click right here, it says normal table, negative infinity to negative z. If you click on it, you see this looks like the values from your standard normal distribution table A. Okay, so sometimes, you know, you can just click it and copy it, or click it and it'll go into the blank, but you can use that. The only problem with using this is, you know, if you use a table that's printed out, then you can make sure you get on the right column. You just kind of have to put your mouse over the right column and then go down to where you need to go to. So it has both of those, though. If you click on the wrong one, of course, you know, this one the positive one starts at 0 and then goes down to 3.49. All right. If that's not there, which it will be, but if that's not there, there's a tables button here. If you click on the tables button, over here are all the tables, all the different types of tables that are used in a statistics class. And so you would have to click on the standard normal table, and then either click on the negative infinity to z, or negative infinity, or infinity to z, or infinity to negative z. So I wouldn't click on this 0 to z. That's a little different from the way that I teach it. Okay. So, but they are here for you in the homework if you need them. All right, so we're going to work this problem next. So you're guaranteed to have a homework problem like this one. I'm going to copy it out and make it a little bit bigger so you can read it. All right, so I'm going to give you a minute to read through this problem. And as you read through it, write down your mean and write down your standard deviation. All right, so this says, and all of us have to do this from time to time, whether we're checking out at a store, whether we're waiting at the doctor's office, you know, we have to wait. That's just part of life. It says time spent waiting in line is approximately normally distributed. The mean waiting time is 6 minutes, and the standard deviation of the waiting time is 1 minute. Find the probability that a person will wait for more than 7 minutes. And the more than is very important in this problem. Okay? So we're figuring out the probability that x is greater than 7. So we need to, so that means x equals 7 for us. We need to figure out the z-score first. So z equals x minus mu over sigma. All right, so that's going to be what? 1.00. All right, now why is the more than important? So here's our standard normal distribution. Let's pretend. Let me move my line a little bit. Okay. And so if I go one standard deviation to the right, I'm going to say it's probably about right there. So this is where z equals 0. This is where z equals 1.00. And for us, that's where x equals 7 minutes. We don't have to write that down there, though. Now, since this is a more than or a greater than problem, I want to take the area to the right. That's what greater than means for us with probabilities. So I told you that's not the way that our tables work, though. So what we have to do here is we have to say 1 minus the probability that, and now I can put my z in here if I want to. Z is greater than 1.00. You could put the x there, but that means the exact same thing. So the reason why I do that is because if I look up 1.00, remember that gives me the area from the far left up to that point. Since I know the area under the curve is equal to 1, if I subtract out all of the stuff to the left, that will give me the area on the right side. Okay, so let's look up 1.00 in our chart, and I get 0.8413. All right, so I have 1 minus 0.8413. All right, do that in the calculator and see what you get. 0.1587. So what that means is there is about a 15.87% chance that a randomly selected person, the next person in line, is going to have to wait more than 7 minutes. It's kind of neat how that works. So if you have, and to get these types of data, to get standard deviations and means, you have to collect huge sets of data. All right? So, because if you just selected a couple people, the mean and standard deviation wouldn't mean much. But if you sat there for a month and you took down the time that it took each person to be weighted on, and then you use something like this, you'd be able to find pretty accurate probabilities. Okay? So with greater than problems, remember I said you need to always worry about the area to the right. For less than problems, if it's a less than, we can just take the area from the table, because that's the way, less than to the left, that's the way our tables work. And then we've already worked a couple between the two, where you have to find the two areas and subtract you have to say the bigger area minus the smaller area. All right, let's do a less than problem, though, just to make sure that we understand that. Any nurses in here, or pre-nurses in here, interested in maybe delivery? Baby delivery? What would that be? What's that section of the hospital where they keep all the babies? Call the section of the hospital where they keep all the babies? Like neonatal care or something like that? I don't know what it's called. Thought I had more nurses interested in medicine and things like that in here. Maybe not. Anyway, here's an example that, if that's something you're thinking about doing one day, I'm sure that you'll have to learn how to do it one way or another at some time. But it says the weights of newborn baby boys born at a local hospital are believed to have a normal distribution with a mean weight of 4,023 grams and a standard deviation of 471 grams. So that's where I get my mean and I get my standard deviation. It says, find the probability that the weight, if we just randomly selected one, would be less than 4,870 grams. Okay. So that's our X, 4,870, and this is a less than problem. Okay, so our Z-score is Z equals 4,870 minus 4,023 over 471. All right, so let's round that to 2 places. So if I rounded that to 2 places, that would be 1.80. All right, so what this actually means, if I was looking at all the area under the curve, remember right here in the middle we have Z equals 0. This is 1.80 standard deviations to the right. So it would probably be somewhere about like this. I'm just going to guess. We'll say Z equals 1.80. Since this is a less than problem, we need the area to the left. And that's the way that our table A and B work. They always give us the area cumulative from left to right. So all we have to do is look up 1.80, and I get 0.9641. 0.9641. That's the area, so that's my probability. So I read an article the other day where there was recently a baby girl that was born in New York that weighed 15 pounds. 15 pounds and I think 23 inches long. So yeah, that's a pretty big baby. All right, so that's not too bad. Now let's skip over a little bit and let's look at how to find a X value if we have the mean and the standard deviation. And we have the probability. So right now we're figuring out probabilities. So let's work a problem where, let's say we have the probability, we have the mean, and we have the standard deviation, but we want to know what X value would that correspond to. Okay, so let me pull up a problem from your book. So we're not doing the exact same thing here. Okay, we're not, our formula that we use for Z-scores, if we're looking for probabilities, we use a Z-score formula. X minus mu. Oh. x minus mu over sigma. Now, if we want to find the x value, though, I would have to take this formula and solve for x. And so the way that you can do that is you can cross multiply if you just put z over 1. And you'd have z times sigma equals 1 times x minus mu. And so if I'm trying to solve for my x value, which would be like the baby's weight or the time waited in line, those x values we were looking at, then I'd have to add mu to both sides. So I do that to get rid of it there. And so now I have x equals z times sigma plus mu. Or the z-score, which we've been using to find probabilities by looking up areas from z-scores. So z-score times the standard deviation plus the mean will give us the x value. All right, so give me just 1 second. I'm going to write this problem down. It is in the PowerPoint, if you look at the PowerPoints. If a normal distribution has a mean of 28.0 and a standard deviation of 2.5, what is the value of the random variable x that has an area to the right equal to, that has an area to the right equal to 0.6700. So what we're trying to figure out is the x value. And in this x value that I'm looking for, about exactly 67% of the area will be shaded to the right. Okay? We know that the total area under the curve is 1, so we may have to use that to help us figure out some stuff that we need to know. So for us to solve for x, for a random variable x, we need 3 things. We need a z-score, we need a standard deviation, and we need a mean. This problem gave us that the mean was equal to 28.0 and the standard deviation was equal to 2.5. So what do we need? What's the last thing we need to find x? We need the z-score. This problem does not give us a z-score. It does give us an area. Okay? Now, the way that our tables work, our tables, if we look up a z-score, will give us the area cumulative left to right. So even if I use my tables, I can't use what it gives me because it told me that the area to the right is equal to 0.67. I need to know, to be able to find a z-score in my table, I need to know the area to the left. Well, if we know that the total area under the curve is 1, then I can say 1 minus 0.67, and that will give me the area to the left. So that's what? 33. Now, before you take your table and you go look for a z-score of 0.33, we're not looking at z-scores right now. This is area. So what we have to do is we have to use our table, and you know all those numbers inside the table? We need to get as close to 0.33 as we possibly can in the table. and then see which z-score that corresponds to. Okay? So if I look on the negative side, and we're looking at the numbers that are 0, point, and then 4 digits, the area numbers. We're trying to get as close to 0.33 as possible. So I see 0.3300. Look in the table. This is table A until you see 0.3300. Now, what is the z-score that corresponds to? Negative 0.44. If you don't see that in your table, then you need to raise your hand and let me come by and show it to you, because this is very important. So if you look on the negative, you look as close to 0.33 as possible. 0.3300 be negative 0.44. Right. That's why it's important you have these tables. I mean, you can pull them up online, but it's a lot easier when it's printed out. Okay. So you have to use these tables to do this. There is no quick fix. There is no punch two things in a calculator and hit enter. Okay? So you have to learn how to use these tables. This is just 2 tables. By the time we get through with statistics, we're going to go through about 10 tables. Okay? This is the easiest 2 to use out of the 10. I promise you. All right. So that's still not my answer, though. I'm looking for the x value that has all of this information, has a z-score of negative 0.44. So I'm going to plug it into this formula here. X equals negative 0.44 times sigma, just 2.5, plus the mean, 28.0. All right. So negative 0.44 times 2.5 equals plus 28.0. So 26.9. So if we have probabilities, or we have these decimals like they give us, we can figure out all kinds of x values by using these tables. Now, we talked a little bit about percentiles a few sections back. Some of you probably didn't care very much for it. Percentiles, though, are percentages. Like the 10th percentile would correspond to an area of 0.1 under the curve. The 50th percentile would be right there at 0.5, would be the area under the curve. Now, percentiles are not z-scores, but percentiles do correspond over to z-scores. So if I use this table, the tables A and B, and I want to find the z-score that corresponds to the 10th percentile, then all I have to do is look at my table and get as close to 0.1000 as possible. So what would the z-score be for the 10th percentile? So it may not be exactly 0.1000, right? Because percentage-wise, the 10th percentile is 10%, which is 0.1000. And so as close as we can get to that, do you see the closest number? Because that's tenths, hundredths, thousandths. It goes to 10 thousandths in this table. So if you look and find 0.1003, that's as close to 0.1000 as we can get. The number on the left is 15 ten-thousandths away. The number on the right is 20 ten-thousandths away. But 0.1003 is only 3 ten-thousandths away. So that's as close to 0.1 as we can get. So what would be the z-score that would correspond to that? Negative 1.28. That's the z-score that corresponds to the 10th percentile. All right, so that will allow us to work out problems that give us percentages. Okay, because percentages, percentiles, they're really all the same thing. We just have to understand what percentile means. Okay, so let me find a percentile problem. I know there's one in your PowerPoint. All right, and this one is dealing with body temperature. All right, it says the body temperatures of adults are normally distributed with a mean of 98.6. All right, everybody in here pretty much knows that, right? You have a temperature over that, you got if it's a little bit, it's a low-grade fever. Some people, like myself, mine is not 98.6 normally. Mine's usually around 97.9 or 98.0. So some people it varies, but overall we have a mean of 98.6 as a population. At least studies have shown that. And a standard deviation of 0.73. What temperature represents the 90th percentile? Okay, so the temperature, that's going to be our x value. That's what we're trying to find here. So x equals z times sigma plus mu. We have sigma, we have mu, we just don't have z. So what are we actually looking for? Well, if I was under this bell-shaped curve and I wanted to know what the 90th percentile is, the 90th percentile is going to be located over here, and it's going to, what does the 90th percentile do? It separates the top 10% from the bottom 90%, right? Because there's 100% all together. So this that I have shaded up here, that would be the bottom 90%, and to the right of that would be the top 10%. Okay? So what does that mean? That means that under the curve, all of this that I have shaded is 0.9000. That's 90% of all the area, 0.9000. So I need to find a z-score that is as close as I can get to having an area of 0.9000. Okay, so you're going to have to look on the positive z-score side. And then look out to the 10,000ths, because the number that I found is not exact, but it's closer than the one on the left or the right of it. And it's going to be what? Positive 1.28. That's 0.8997. 0.8997 is very, very close to 0.9000. It's 3 ten-thousandths away. Man, that's about the same as what we just did with 10, the 10th percentile, isn't it? There is a relationship there because of symmetry. But the z-score that we would get is z equals 1.28. All right, so our x value, we want to know what would the 90th percentile temperature be. It's going to be x equals 1.28 times 0.73 plus 98.6. All right, so that's what we need to do in the calculator. And what does it say round to? It doesn't tell us to round. I'll just write my answer down like that then. 99.5344. But usually a problem like this would tell us to round. What that means is 10% of our population has a temperature higher than that. 90% of our population has a temperature lower than that. So for some people, having a temperature of 99.5 is normal. Okay? Only 10% of the population, but for some people that's normal. All right, so if you're working problems and it starts talking about percentiles in the problem, even if it says, you know, there may be a problem that you're going to work, and I remember seeing one in the homework like this. It wanted to know, like, which x values would separate the top 20% from the bottom 80%. Well, the top 20% would mean the area on the right is 0.2. From the bottom 80%, that would mean the area on the left is 0.8. So remember, these aren't z-scores, though. If you're getting percentages in the problem, they're not z-scores. They are probabilities. And so if they're giving us those values, we're looking for x values. So if we're looking for x values, we have to use this formula here. All right, and remember, the way that our tables work is that the tables are going to show areas cumulative left to right. So if I wanted to know what z-score corresponded to the 80th percentile, then I would have to look up an area of 0.8000, or get as close to it as I possibly could. So if I do that, that's 0.7995. That would be a z-score of 0.84, positive 0.84. Now, if we're trying to figure out the probabilities, though, that's where we use our z-score formula, z equals x minus mu over sigma, and get a z-score, and then we can look up that value in the chart. And depending on whether it's a less than problem or a greater than problem or between two values, then we have to use whichever chart. I mean, we have to use those values whichever way we're supposed to use them. Sometimes if it's a greater than, it's 1 minus the area we have. If it's a less than, we take the value from the table. And if it's a between the two, you find the two z-scores, find the two areas, and say the bigger area minus the smaller area. Okay. Now, a long time ago, and this is moving on to the next section. A long time ago, we didn't have calculators. Not even that long ago, really. Okay? If you ever look up like some of the first calculators, they'll be as big as this room. Seriously, it was crazy. Even the first portable calculators that won't do any of this fancy statistics stuff, they were still several pounds. They were huge. Okay? And they were very, very expensive. Well, before we had calculators to help us with, do you remember the binomial distribution? The binomial distribution was, we had to use that formula. Do you remember it? Maybe a little bit. Think about what was the binomial formula? NCX times p to the x times 1 minus p to the n minus x. Well, these problems you can work out pretty easily, work out that combination, but back in the day, a long time ago, if these numbers got big, then they had a lot of work to do. So like, if n is equal to, say, 1,000, your calculators only give you an approximation when you do something like this. And if x was equal to 500, and then we had, say the probability of success was 0.25, and that would mean I would have to take 0.25 and raise it to the 500th power. And then I'd have to say 1 minus p, that would be 0.75 to the n minus x, and so that would be to the 500th power. That would take a very long time to do. I mean, just look at it. It would probably take you hours and hours and hours, and that's if you're really good and make no mistakes. So what people had to do back then to approximate a binomial distribution when these numbers are really large is they used these charts, okay? And they converted the values over to z-scores. Because have we been working with super big numbers with z-scores? No. The z-scores have been all between, I think, even our tables show us between negative 3.49 and positive 3.49, because that's almost all the area under the curve. So if we're able to standardize numbers by doing what we were doing earlier, then we can use that to approximate a binomial distribution. Now, approximate doesn't mean give you the exact answer, right? An approximation is sometimes good, it's sometimes not that good. But if I'm dealing with numbers like this, an approximation is going to be okay. Okay? So, one thing that your book doesn't do is give you like a chart to go by for these approximations and what we have to do. We're going to be doing the same stuff that we were doing with converting z-scores over, finding area under the curve, but it's going to depend on whether, you know, if we have a less than problem, a less than or equal to problem, a greater than problem, a greater than or equal to problem, we're going to have to add or subtract 0.5 from whatever our value is, our x value, okay? And since your book doesn't give you this table, I printed this table out for you. Now, if you're watching this video right now, you might want to take a screenshot and put that in your notes, because you can find it online. I found the formulas, and then right underneath the formulas was an example of what to do when x equals 6. You know, of course, every problem's not going to have x equals 6, but it tells you which x values to use depending on if it's an equal to problem, a greater than problem, a less than or equal to, a less than or a greater than or equal to. I'm going to hand this out real quick. I would put this probably with your formula sheets. You have to use this specifically on 8.6, and you may never use it again. Because, again, this is just how to approximate the binomial distribution problems. Now, after we know what to plug in for our x, though, we have to look if it's a less than problem, a greater than problem. Nothing changes. We still do all the same stuff that we were doing. Now, could we work out a problem when x equals to 6 using our binomial probability distribution? Yeah, we could work that out pretty easily, more than likely. But this also works when the numbers get so large that your calculators can't even store the answers. We can approximate by using the same methods we were just using with normal distributions. All right. So, let me pull up us a problem really quick. Here's one, and we're not going to do this one. Don't write this down. But your book goes through a problem You know, where I use these values right here, it says, basically says, back in the day, we couldn't do this right here very easy. That would take us all day long and probably the next day. There may be some shortcuts, but when you start multiplying all those numbers out, doing that combination, they get astronomical. Okay? However, by using the tools that we have now with normal distributions, we can make that problem at least find a approximation to the answer, what the actual answer should be. So, let's see if we can quickly work through these two problems. Let me make sure we don't need any more information. So here's the problems. This is out of your ebook. So this is an A and a B. All right, so what we're trying to do is we're trying to figure out if x is 5 or less. Now, I'm not sure if you remember the formulas for mean of a binomial. Do you remember that? You probably don't because they're on your formula sheet. But for binomial distributions, usually the way we calculate the mean, that's the same as the expected value. That was just equal to n times p. All right? And the way that we find the standard deviation, and we went over this a while back, is the square root of n times p times 1 minus p. So we will need those to help us find our z-scores, or, you know, because we need a mean and we need a standard deviation. So this problem tells us n equals 40 and p equals 0.5. Okay, so the first thing I need to do is calculate the mean and standard deviation. So for part A, and I believe it's going to be the same thing for part B as well, we're using the same number, so we only have to calculate this once. So mu equals, n was 20 times p is 0.5. So the mean is what? 10, right? Because 20 times 0.5 is 10. All right. So now, if we want to do 5 or less, let's look back over at our chart. 5 or less means less than or equal to, right? 5 or less means less than or equal to. So for a less than or equal to problem, it says we want to find the probability that x is less than n plus 0.5. All right, so if we add 0.5, because it's a less than or equal to problem, then what is our x going to be equal to? We add 0.5. It's in rocket science, is it? 5 plus 0.5. 5.5. So now we have everything we need to find our z-score. So z equals x, which is 5.5, minus mu, which is 10, divided by sigma, which I haven't found. So let's find that real quick. Sigma equals the square root of 20 times 0.5 times 0.5, because 1 minus 0.5 is 0.5. So I'll punch that in the calculator for us. 20 times 0.5 times 0.5, and then I have to take the square root. So the square root of 5, I'm going to take that out to about I like to take things out kind of far, so I'm going to take it out to at least 4 decimal places, because remember, we round the z-score to 2 decimal places. So 2.2361 is what I'm going to use. All right, so in my formula, I have x minus mu divided by sigma. Now remember, our z-scores have to be between around negative 3.5 and 3.5. If I work this out and I get 12 as the answer, I messed up. Okay? So they should be, relatively small numbers when I work them out. So 5.5 minus 10 divided by 2.2361. So my z-score, if I round this to 2 places, is negative 2.01. All right, since this is a less than problem, I'm going to take the area to the left of that. So look at your z-score chart that we were using earlier. And let's go to negative 2.01. And negative 2.01, I get 0.0222. All right, so that's an area equal to 0.0222. So that is the approximate probability that I would get a random variable of 5 or less for this data set. All right, for part B, we are looking at, find the probability that x is greater than 4. Okay, so greater than 4, we need to go to our continuity correction table and see what do we do for a greater than. It looks like for greater than, we add 0.5. So we do the same thing we did last time. We're going to add 0.5. All right, so if we say 4 plus 0.5, the x that we're going to use is 4.5. All right, we have the same mean and standard deviation as before. All right, so let's find the z-score. So it's x minus mu divided by sigma. All right, so let's do that in the calculator. 4.5 minus 10 divided by 2.2361. So we have a z-score of negative 2. Got to run this to 2 places. Negative 2.46. All right. Since this is a greater than problem, we need to find the area to the right. All right, so if I was under my standard normal curve here, remember z equals 0 is here in the middle, and negative 2.46 standard deviations to the left. That's what the negative does. So, that's going to be way over here. And this is, of course, just a guesstimation, but that's about where it would be. And since this is a greater than problem, we're trying to figure out the area to the right of that because it was greater than. But that's not the way that our tables work. All right? Remember, our tables are cumulative left to right. So if I look up the negative 2.46, it's going to give me the area right here from the left up to that point. So what I need to do is I need to say 1 minus this little part, and that will give me everything to the right of that. So if we had to guess, I'd say we're going to be subtracting out something really small, and when we get our answer, it's probably going to be 0.9 something. I'm just guessing, though. So what you need to do is now we go to our standard normal table chart. All right. In your table, if you go to negative 2.46, you'll see a value of 0.0069. All right. So that's a super small area to the left right there. But if we say 1 minus that, say 1 minus 0.0069, that will give us the area to the right. All right, so that's 0.9931. And that area corresponds to a probability. So what's the probability that x is greater than 4? 0.9931. Now, again, that's just an estimation. It's an approximation. It's not the exact. If you work this out using the binomial probability formula, you're not going to exactly get this. You'll probably get something close to it. But the thing is, as these numbers get really large, back in the day, it was too hard for them to figure out and work out the problems using the old binomial formulas. So if we use these standard or a normal distribution, we can get an approximation for it.